Now let's discuss two important distributions. One is the binomial, and the limiting situation of the binomial distribution is the Poisson distribution. Till far, we have looked at distributions for continuous random variables, that is normal and exponential, and also some of the general continuous distributions we have looked at. Now let's try and look at the binomial distribution. So one is familiar with this particular formula even at the +1 level, because when I say I want to calculate the probability of a particular event or a particular thing, let's say px, then that is given by this formula, meaning you can always calculate out of n possibilities if you want x possibilities, and that possibility has a success probability, let us say of p, then it is px, and the failure probability, which is also 1 minus success probability or sometimes represented by q, would have n minus x. Because if I am saying that in x situations I'm going to succeed, then obviously in n minus x situations I'm going to fail. So this becomes the expression for binomial probability. That is, if I'm talking about an experiment, a probability experiment, where there are n trials and I want success in x trials, and this is what is going to happen. Why NCX? Because I can choose any x cases out of n cases where I'm going to succeed, and that is where the probability of success would be p power x, and that should be multiplied by probability of failure, which is q into n minus x, because I'm succeeding in x cases and I'm failing in n minus x cases, right? Succeeding in x cases, failing in n minus x cases. And this, if I consider for all possible x's in that experiment, then this is going to constitute, that is set of probabilities are going to constitute the binomial distribution. So now we have chosen one experiment, that is tossing of a fair coin, and how many trials we have taken? There are 10 trials. Now if I ask what is the probability of getting either a head or tail, this is a situation where both probabilities are equal, and it is equal to half. Whether you are talking about the probability of getting a head or probability of getting a tail in a particular tossing. So therefore if I choose 10 trials to describe this particular experimentation, then there are these possibilities, 11 possibilities that I can talk about for the occurrence of head. When I talk about 11 possibilities, what are those? Either you can have a situation that you are going to have 0 heads in all the 10 tosses that you carry out. That means you will get tails in all the 10 tossings. Or you can have a situation where there is only 1 head occurring out of 10 trials. There can be 2 heads that can occur in 10 trials, 3 heads that can occur, 4 heads. Similarly, you can have 10 heads. That means every time that you toss, you get a head. So therefore, these probabilities are calculated. How do you calculate? Now it is very, very obvious. For example, if I am talking about 0 heads out of 10, you have no success whatsoever, 10C0, and then half to the power 0, and the failure probability is also half, unfortunately or fortunately, so that is going to be 10 minus 0. But remember, in this case, one advantage is if I add, since the probabilities are equal, success and failure probabilities are equal, if I add the power, that will simply give me the number of trials, right? So therefore, if I am talking about any other situation, say 1 head, then that also would be exactly the same. So that is also would give me this, because 1 plus 9 is always 10. Success probability to the power 1, because you are seeking one head, and failure probability to the power 9, because in 9 cases you are failing. And why do I get 10 such possibilities? Because the occurrence of head cannot be restricted to any one trial. It can occur in either the first trial, second trial, third trial, up to 10 trials. So that is why this 10C1 factor comes into P. Similarly, if I talk about 2 heads, I can say 10C2. These 2 events can occur in any of the 1 to 10 trials. That is why it is 10C2. And you can have half to the power 2 because there are 2 successes, and half to the power 8 because there are 8 failures. And this is how probability is calculated. Success probability raised to number of success, failure probability raised to number of failures, and then how many trials, how many possibilities the success can occur. Because when I talk about 10C2, what are the possibilities? Either in the first 2, either in the first and the last, either in the first and the penultimate, that is n minus 1, or I can have success in the middle and success in the last. So you can have several combinations, and that is what 10C2 is actually telling you. So therefore, we have calculated the probabilities for all these values of the discrete variable, and here the definition of the discrete variable in this experiment of probability is the occurrence of number of heads. Am I right? Occurrence of number of heads. It can be either 0, 1, 2, 3, 4, up to 10. So this is the description of the random variable that I am talking about, and the distribution that we have developed is for these random variables. And you might see that the probabilities that have been represented here for various x's, that is for various values of the random variable, are joined by a smooth curve, and there is a purpose to it. You might argue that this is not for a continuous random variable, rather it is for a discrete random variable. But why have I joined those points? And I have arrived at a very, very interesting shape, a shape that is highly familiar to you, because I am referring to the normal or the Gaussian distribution, where the probability density curve assumes the shape of a bell. Am I right? And the same thing you are seeing here, but however, here I cannot define probability for any value x other than the integer. I cannot say I can define the probability for x equal to 5, which is the highest probability, but if you ask me to define probability anything between 4 and 5, I cannot define, because this probability curve, whatever we have developed, it is for a discrete random variable situation. But then what does the central limit theorem state? Because that is perhaps the most important theorem in statistics, and it tells you that as you have more and more trials in a binomial probability experiment, then what happens, this curve which you are going to develop by joining all the probabilities for various trials for the random chosen random variable would mimic or would take after to a very, very great extent with normal distribution. That is, it would become almost the bell curve. Then how do I interpret that? Because here I am talking about discrete random variable, but when it comes to normal distribution, I am talking about continuous random variable. Where is the match? Of course, we are going to have one detailed numerical for a particular probability experiment predicting values from both normal distribution assumption as well as from binomial distribution. But the point here that we are trying to drive home is very, very important. There are 2 parameters that we have been emphasizing for a distribution, whether I am talking about distribution for discrete or continuous. What are those? Those parameters are mean and then variance. In a while, we are going to derive the expression for mean and variance of binomial distribution. Of course, for binomial distribution, mean is going to be given by n into p, where n is the number of trials and p is the success probability. And when it comes to variance, it's going to be given by NPQ, where Q is the failure probability, P is the success probability, N is the number of trials. So these two are going to be established. The point that we are trying to suggest here when I say that this curve is going to be almost coincident with the normal distribution is that the normal distribution would have mean and variance equivalent to the one that you can calculate for this discrete random variable. Because in order to develop the mathematical definition of a Gaussian distribution or bell curve, you require mean and variance, right? Because if I recall the expression, what is that? 1 by root of 2 pi, the standard deviation, e power minus half x minus mu by sigma whole square. Do you appreciate that sigma and mu? That means mu is the mean, square of sigma is the variance. These are the two parameters that are required to define the Gaussian distribution or the probability density curve or function. And therefore, if NP of the binomial distribution becomes almost equal to the mean of this and NPQ becomes the variance of this, then obviously the curves are identical to each other. So this is what the central limit theorem says, that as the number of trials increase, and when you develop this particular plot, you would appreciate that the Gaussian distribution and the binomial distribution take after each other very, very close. Which Gaussian distribution you are talking about? The one that has the equivalent mean and the equivalent variance of the binomial distribution. So that is the message that we would like to impress upon. So now let's go ahead and develop an expression for mean and variance of the binomial distribution. Of course, we have the formula, but since this is a discrete random variable situation, we do not require any integration whatsoever. It would be summation and then some algebraic manipulations, and then you would be home with the required result. So let's move on and compute the mean for binomial distribution followed by the variance.